In the vast tapestry of the cosmos, there exists an entity so mystifying, so arcane, that even the brightest minds have grappled with its very concept. We speak, of course, of the elusive black hole. These cosmic enigmas have often been portrayed in popular culture as ravenous behemoths, lurking in the shadows of space, waiting to devour any and everything in their path. But the cinematic depictions only scratch the surface of their true nature. For the first time in recorded history, brave scientists have pierced the veil, venturing into the very heart of these galactic maws. What secrets lie in their abyssal depths? Could the inside of a black hole harbor truths more petrifying than any sci-fi narrative? Join us, dear reader, on this foray into the belly of the universe's most enigmatic beast. There's an eerie, unsettling quality to black holes. This seemingly endless void tugs at our very understanding, suggesting a realm where time itself becomes moot and our very understanding of reality is tested. The very essence of a black hole eludes even the most astute thinkers. What, then, is this celestial anomaly that seems to defy the very laws of physics? At its core, gravity. But to simply chalk it up to gravity would be an oversimplification. There's an even more captivating tale. Born from the cataclysmic collision of star remnants, when their mass begins to surpass thrice that of the Sun, black holes emerge as the undisputed titans of gravitational might. Their gargantuan pull is so overwhelming that they entrap even beams of light. It's a belief held by many astronomers that at the heart of most spiral and elliptical galaxies, there lurks a black hole, silently dictating the dance of stars. Yet, not all black holes are forged from the same cosmic crucible. The stellar mass black holes, mere infants in the grand scale, weigh between once and 100 times the mass of the Sun. They rise from the ashes of supernova, cataclysmic death throes of once majestic stars. Then there are the behemoths, the supermassive black holes. With masses ranging from millions to billions of times that of the Sun, they are believed to grow by assimilating other black holes and consuming unsuspecting stars. The intermediaries, as their name implies, lie in between. They are the shadowy figures with only a handful spotted, each suspected of holding mass between 100 and a staggering 100,000 suns. They might just be the progenitors of the supermassive entities. Beyond their enigmatic nature and cosmic ballet, black holes hold keys to unlocking new dimensions in physics. They challenge our understanding, defying Einstein's theory of general relativity. According to this revered theory, as matter is drawn into a black hole, it vanishes, leaving no trace. But quantum mechanics stands its ground, asserting that such a disappearance is impossible. This schism between the two Titan theories presents a tantalizing puzzle, a theoretical battleground for mathematicians and astrophysicists. In essence, black holes aren't just galactic anomalies. They are cosmic gatekeepers, challenging us to unlock the mysteries of the universe itself. And as we delve deeper into their secrets, one can't help but wonder, what other enigmas await in the heart of these abyssal giants? As we further our exploration into the heart of these cosmic riddles, we discover that black holes serve as proving grounds for some of the most groundbreaking theories that aim to decipher the universe's enigmatic code. From the famed general relativity to the intricate webs of quantum physics and string theory, these voids challenge our very understanding of the cosmos. Contrary to popular belief, black holes are not merely holes in space. Imagine, if you will, a celestial supermagnet. Rather than pulling metals towards it through magnetism, this cosmic supermagnet uses extreme gravity to attract, well, everything. It's this very gravity that ensures we remain anchored to our beloved Earth, ever pulled towards its core. On the surface, Earth's embrace stops. But in the inky void of a black hole, no such surface exists to halt your descent. It's as if you're eternally plummeting into an abyss, giving rise to the term black hole. A black hole's inception is a thing of cosmic grandeur. Picture a star, massive in its glory, imploding into itself and condensing its vastness into a tiny expanse. This implosion leads to an incredibly dense core, a star's entirety crushed into an almost inconceivable space. Given that all matter exudes some gravitational force, this compressed mass results in amplified gravity. For instance, while the Earth gently beckons you towards it, you too, albeit in an infinitesimally minor manner, pull the Earth toward yourself. But of course, Earth's colossal mass compared to yours makes its pull supremely dominant. Similarly, when compared to the Moon, with its smaller mass and weaker gravitational allure, astronauts experience a sensation of weightlessness. To truly grasp a black hole's mind-wrenching compression, visualize our Sun, with its majestic span of approximately 1.4 million kilometers, collapsing into a realm the size of a quaint town, merely about 10 kilometers in length. The magnitude of this compression is akin to shrinking the iconic Eiffel Tower to a singular grain of rice. Therefore, labeling them as mere holes is a misnomer. It's less about their structure and more about the engulfing effect they exert upon their surroundings. At the heart of this cosmic enigma lies its two essential components, the singularity and the event horizon. The singularity, nestled at its center, is an almost mythical point of infinite density, drawing everything into its core. Surrounding this core is the event horizon, often portrayed in films as the ominous dark circle, acting as a threshold of no return. But this isn't a tangible barrier. It's an invisible boundary beyond which even light cannot escape. Thus, we do not see black holes in their entirety, but only perceive their overwhelming effects on their surroundings. In 1915, the genius of Albert Einstein postulated that objects moving through space created ripples in spacetime, a concept that wed space and time. A century later, in 2015, this groundbreaking hypothesis was vindicated when the Laser Interferometer Gravitational Wave Observatory detected waves resulting from a black hole collision that occurred an astonishing 1.3 billion years ago. Black holes may elude our eyes, but their effect on nearby entities is glaringly evident. In a revolutionary achievement, the Event Horizon Telescope, a consortium of 8 terrestrial radio telescopes, in April 2019, unveiled the inaugural image of a black hole located in the galaxy Messier 87. This black hole, a staggering 55 million light-years away and a breathtaking 6.5 billion times as massive as the Sun, revealed a luminous ring, the radiant aftermath of gas drawn to the event horizon. However, despite our strides in understanding black holes, their interiors remain shrouded in mystery. What awaits those who dare to venture into their depths? While curiosity might tempt one to dive into this abyss, the prognosis is grim. Be it the terror of spaghettification in a stellar mass black hole, where one's body is compressed and elongated to resemble spaghetti, or the relatively less gruesome fate in a supermassive black hole, the verdict is clear. Venturing into a black hole is a one-way ticket to the unknown, with no hope for return. Sagittarius, a star, is a strikingly appealing candidate for such a one-way journey of exploration. Positioned right at the heart of our Milky Way galaxy, it is a supermassive black hole that spans a vast 44 million kilometers. It holds an astonishingly heavy load, equivalent to roughly 4.31 million times the mass of our Sun. This massive celestial object was first discovered by astronomers Bruce Ballack and Robert L. Brown in the year 1974. However, it was only in 1982 that it was christened with its unique name. As you venture deeper into Sagittarius, a star, the real adventure commences once you traverse the event horizon. This is the proverbial point of no return. From within, the universe outside would still be visible to you. Yet, to any external observer, you'd be lost, as any light attempting to signal your presence would only bounce back towards you. On the bright side, while the gravitational intensity within a supermassive black hole is considerably powerful, the stretching forces, or tidal forces, are reduced. This means you'd be spared the unnerving fate of being elongated like spaghetti. But before you heave a sigh of relief, there's bad news. Escape is virtually impossible. Or is it? Some believe in the concept of the white hole. In layman's terms, if a black hole is like a vacuum that pulls everything in, then a white hole is its antithesis, expelling things out. They are somewhat like two sides of the same cosmic coin, possibly connected by an intricate interdimensional passage known as a wormhole. Optimistically, if you happen to linger in a black hole long enough, it might just metamorphose into a white hole. Though this transformation could span billions of years, the intense gravitational forces might make it feel like a mere blink of an eye for you. But one must tread with caution. This is still a theoretical arena, and science is constantly evolving. Delving deeper into the enigma of black holes, it's intriguing to ponder what really transpires within. For an adventurer trapped within, one could potentially contribute to the vast expanse of human knowledge by embarking on scientific experiments. There's a hypothesis that within a black hole, matter isn't compacted into an infinitely minuscule point. Perhaps there exists the smallest conceivable configuration of matter, referred to as a Planck star. This concept has its roots in loop quantum gravity, a speculative theory aiming to marry the quantum world with gravity. In this proposed framework, spacetime is granular, made up of minute, distinct chunks. These minuscule chunks of spacetime might just be the saving grace, preventing singularities within black holes and eventually leading to their explosive end. The gravistar, another concept stemming from the theoretical realm, offers an alternative to singularities. The name might sound a tad cobbled together, but then, astronomy has its quirks. A gravistar differs from a black hole in its contents. Instead of a singularity, it's brimming with dark energy, the mysterious force responsible for the accelerated expansion of our universe. Any matter that approaches a gravistar can't penetrate the event horizon due to this overwhelming dark energy, so it remains on its surface. However, recent observations hint at gravistars being a less probable entity compared to black holes. As intriguing as Planck stars and gravistars sound, they aren't the only theories in town. Scientists speculate that the core idea of an infinitely dense point might stem from our understanding of a rather rudimentary black hole. In reality, black holes are much more dynamic, especially when in motion. The spin of a rotating black hole could morph the singularity into a ring. And if Einstein's theory of relativity is anything to go by, crossing through this ringed singularity might catapult you into a wormhole, dropping you off in a brand new universe. However, this is accompanied by the caveat that the interiors of such rotating black holes are incredibly unstable. In essence, the universe and its vast expanse hold mysteries that we're only beginning to scratch the surface of. Black holes, with their enigmatic nature, beckon scientists and enthusiasts alike, promising secrets that could reshape our understanding of reality. The fascinating world of rotating black holes is a realm of extremities and unpredictability. The singularity, which is stretched into a ring, whirls around at a speed that's almost unfathomable, producing a centrifugal force of colossal magnitude. This force, when integrated into the framework of general relativity, functions more like an anti-gravitational force, pushing instead of pulling. This enigmatic behavior manifests in the creation of an inner horizon nestled within the black hole. This horizon acts like a boundary, with radiation from the universe's vast expanse hurtling inward, being irresistibly drawn towards the singularity due to the formidable gravitational force. However, juxtaposed to this phenomenon is the radiation that experiences the push from the anti-gravity in proximity to the ring singularity. This intricate dance of opposing forces with the inner horizon acting as the fulcrum results in a moment of sheer intensity. Imagine encountering the inner horizon. You would be faced with a burst of radiation so potent that it would seem like the entire chronicles of the universe are being conveyed to you in an infinitesimally small moment. Yet, there's a conundrum here. Rotating black holes are not just figments of our imagination. They very much exist in the vastness of our cosmos. This existence casts shadows of doubt on our mathematical models and points towards mysterious underlying phenomena. Enter gravitational waves, a groundbreaking concept that has allowed us glimpses into the interiors of these dark, mysterious giants. In 2015, the scientific community celebrated the inaugural discovery of gravitational waves. These ripples in the fabric of space-time, born out of cataclysmic collisions between black holes, gave scientists an auditory means to decipher the universe's secrets. Picture shaking a mysterious container and discerning its contents based solely on the sounds emanating from it. That's what scientists did, metaphorically speaking. With the reverberations of almost 100 colliding black holes registered, researchers are tirelessly working on refining their models of these majestic cosmic events. Through this meticulous research, the aim is to further understand and map the intricacies of black hole structures and assess how Einstein's celebrated theory of general relativity stands when confronted with such extremities. The studies and models that have been predominantly used until now have had their foundation in linear interactions. While effective to some degree, they come with their own set of limitations, notably not accounting for some other behavioral nuances. The exploration of nonlinear interactions promises to enrich these models by a considerable margin, potentially up to 10%. This enhancement will bolster scientists' capabilities in detecting even more colliding black holes, thereby deepening our understanding of gravity and the enigmatic events unfolding in the universe's distant realms. Interestingly, while the world grappled with the pandemic, LIGO, the pioneering observatory that first discerned gravitational waves, remained dormant since 2020. However, with the promise of the future, new systems are set to come online, aiming to bring into focus even more details about these dark celestial wonders. Black holes have always been subjects of intrigue, but recent research from the University of Michigan throws another layer of mystery on these cosmic entities. They propose a concept that might seem straight out of a science fiction novel: black holes as holograms. Now, to clarify, this doesn't imply that black holes are mere light projections as seen in popular sci-fi media. The exploration is more nuanced. Spearheaded by Enrico Rinaldi, the research dives deep into the realm of holographic duality. This duality suggests that theories revolving around gravity and particles are mathematically twinned. The world of gravity portrays three-dimensional interactions, whereas particle theory is ensconced in the two-dimensional realm. Black holes, in all their grandeur and mystery, serve as a bridge between these theories. Rinaldi's innovative research merges two simulation methods, aiming to chart the gravitational landscape of a black hole. The pull inside a black hole is so overpowering that visual observations are almost impossible. Thus, relying on mathematical frameworks becomes imperative. Rinaldi likens our perception of the black hole's interiors to viewing a holographic projection. In popular culture, a hologram might remind one of the lifelike projection of the rapper Tupac. The image, though two-dimensional on a Mylar sheet, gives the illusion of a three-dimensional persona. In a similar vein, the research posits that black holes might possess a three-dimensional core, the understanding of which is relayed to us via two-dimensional quantum matrix models. These models bridge the gap between the theory of gravity and particle theory, painting a comprehensive picture of the black hole's dynamics. The ultimate challenge remains in truly understanding and perceiving the innards of a black hole in ways that could revolutionize our grasp of the universe's very nature. And while these mathematical models and theories are indeed captivating, witnessing the raw power of a black hole is an experience like no other. A black hole, previously unbeknownst to astronomers, made its awe-inspiring presence felt when it tore apart and consumed a star that had ventured too close, serving as a powerful reminder of the universe's wonders and mysteries. Recently, a celestial event of immense proportions occurred in the vast expanses of our universe. A star was torn apart in what is scientifically referred to as a tidal disruption event, TDE, by an intermediate mass black hole situated within a dwarf galaxy. This dwarf galaxy, though diminutive in stature, lies at a staggering distance of 1 million light-years from us. The cataclysmic aftermath of this event resulted in the emission of a powerful radiation flare, so luminous that it transiently eclipsed every other star within the confines of its native dwarf galaxy. Such events are not merely awe-inspiring phenomena for casual observers. For the scientific community, this TDE provides invaluable insights, especially in understanding the intricate dynamics between galaxies and the lurking black holes within their confines. Furthermore, this occurrence offers researchers a fresh intermediate black hole specimen for their investigative pursuits. The immense curiosity this event generated within the scientific community can be attributed to its potential in uncovering more such intermediate mass black holes residing in quiet dwarf galaxies and, importantly, in measuring their masses. Designated as at 2020 NE, this TDE flares detection was credited to astronomers working on the Young Supernova Experiment, or YSE. The YSE is a specialized astronomical survey program tailored to identify and study ephemeral cosmic phenomena, such as supernova eruptions. As this black hole embarked on its voracious feast on the star, the precise observation of this initial destructive phase was instrumental. It enabled an international consortium of researchers, with notable contributions from scientists at UCSC and the Niels Bohr Institute's astronomer, Charlotte Angus, to ascertain the black hole's mass. Their estimations revealed it to be somewhere in the vast range between 100,000 and 1 million times the mass of our Sun. Historically, TDEs have been invaluable in determining the masses of colossal supermassive black holes. However, at 2020 NE's swift flare marks a pioneering instance wherein such a methodology was employed to discern the masses of the relatively smaller yet significant intermediate mass black holes. The prompt detection of this transient flare has the potential to set a precedent, serving as a foundational reference for forthcoming studies concerning the masses of mid-sized black holes. One of the profound takeaways from this observation is the unique opportunity it presented to detect a typically elusive mid-sized black hole actively consuming a star. Leveraging the flare's characteristics can elucidate mysteries surrounding this particular subset of black holes, which may very well dominate the cores of numerous galaxies. The realms of astrophysics have long been intrigued by supermassive black holes, gargantuan entities whose masses can dwarf our Sun by millions or even billions of times. The prevalent hypothesis postulates that these behemoths could potentially originate from the mergers of intermediate mass black holes. Supporting this theory, it is believed that the nascent universe was replete with dwarf galaxies, each potentially harboring an intermediate black hole. As cosmic evolution ensued, dwarf galaxies either amalgamated or were assimilated by their larger counterparts. As a consequence, their resident intermediate black holes engaged in a ferocious dance of annihilation, continuously augmenting in mass. This domino effect of cascading mergers would conceivably culminate in the creation of the supermassive black hole titans that preside over most galaxy centers today. However, this grand theory of black hole evolution is punctuated with a pivotal unresolved query. Do all dwarf galaxies inherently possess their own intermediate mass black hole? It's essential to remember that the very nature of black holes makes them an observational challenge. Owing to the event horizon, which engulfs and conceals all light, black holes remain imperceptible unless they are in a feeding frenzy, consuming nearby gas, dust, or engaging in dramatic star-shredding TDEs. It would be remiss not to ask, among the myriad wonders and enigmas of our universe, what facet of black holes evokes the most awe and intrigue in your mind? We invite you to share your thoughts and reflections on these cosmic marvels in the comments section.